Hello, this is Professor Keen. I'd like to finish up my lecture on Helmholtz. And so right now we're on page about 128 in the Student's Guide to the Grade Physics Text, Volume 3. Last time we talked about the mechanical theory of heat and specifically James Joule's experiments that demonstrated that a definite quantity of work produces a definite quantity of heat. He summarizes this then at the bottom of page 128. I'm going to read a short section from here. He says, "Thus then, a certain quantity of heat may be changed into a definite quantity of work. This quantity of work can also be retransformed into heat, and indeed into exactly the same quantity of heat as that from which it originated. In a mechanical," he says, "in a mechanical point of view, they are exactly equivalent. Heat is a new form in which a quantity of work may appear." And then he goes on to say that these facts no longer permit us to regard heat as a substance, so he's being critical of the caloric theory. For its quantity is not unchangeable. It can be produced anew from the vis viva, that's the term that was used at that time for kinetic energy, the living force, so to speak, or moving force. From the vis viva of motion destroyed, it can be destroyed and then produces motion. We must rather conclude from this that heat itself is a form of motion, an internal invisible motion of the smallest elementary particles of bodies. If therefore motion seems lost in friction and impact, it is not actually lost, but only passes from the great visible masses to their smallest particles. While in steam engines, the internal motion of the heated gaseous particles is transferred to the piston of the machine, accumulated in it, and combined in a resultant whole. But what is the nature of this internal motion can only be asserted with any degree of probability in the case of gases. Their particles probably cross one another in rectilinear or straight line paths in all directions until striking another particle or against the side of the vessel, they are reflected in another direction. A gas would thus be analogous to a swarm of gnats, consisting, however, of particles infinitely small and infinitely more closely packed. This hypothesis, which has been developed by Krönig, Clausius, and Maxwell, very well accounts for all the phenomena of gases, or so Helmholtz claims. So he's really pushing this atomic theory and the mechanical theory of heat in this essay. Now, the next thing he does is goes on to explain how this conservation of energy isn't just something that shows up with kinetic energy turning into potential energy, potential turning into kinetic, and either of those turning into heat. It also shows up in many other systems, electrical, chemical, and so on. So he talks a bit about the process of burning. So I want to mention something here. This is an interesting discussion he has about burning of substances. So you might imagine that you have a piece of wood. So here's a log of wood. Okay, and what is the log made of? Well, it has a lot of, if you're a chemist, you know this, it has a lot of carbon in it. So I'm going to draw a few C's in it to indicate that one may extract carbon atoms from the wood. The idea is its matter is made largely of carbon. And if you put it in an environment where there is a lot of oxygen atoms, you might say, that are in the air surrounding it, the oxygen and the carbon are near each other, but they are not bonded to one another when the oxygen is in this gaseous state and the carbon is in the wood. But if you provide a spark, let's suppose you have a match and you light this, you give it a little bit of a push, you might say, with this spark, what is going to happen then is that the oxygen and the carbon, when the oxygen is zipping around in the air, it can bond to the carbon and form a carbon monoxide, that's one carbon and one oxygen, or a carbon dioxide molecule, depending on how oxygen-rich the air is. And when they snap together like that, that is the process of burning or combustion. And when they do so, as these carbon and oxygen atoms, you might say, fall together under these chemical forces. They snap together and they give motion to the carbon monoxide or carbon dioxide molecules, and then those are zipping around at a faster speed than the oxygen particles had been, or the carbon particles had been zipping around before them. That extra motion in the air we understand as heat. So here you have not a gravitational force pulling things together, rather you have an chemical attractive force, an electrical force, if you will, pulling these together, causing bonds to form and generating kinetic energy. And in this case, it's a disordered kinetic energy, and so that is heat. It's a nice comparison he makes between if you pull a mass away from the Earth, you give the system gravitational potential energy. If you release that mass, it falls toward the Earth. As it's falling, that turns into kinetic energy. When it hits the Earth and comes to a stop, then that directed kinetic energy becomes random kinetic energy of vibration, which is heat. Here the same kind of thing happens. You separate the oxygen from the carbon. Oxygen is in the atmosphere or the air. Carbon is in the wood. They fall toward each other, and when they snap together, then that initial potential energy is turned into a kinetic energy, and if it's random, it turns into heat. Now, of course, the carbon dioxide and carbon monoxide can no longer give up any energy for the same reason that the weight of a pendulum clock cannot deliver any more work when it has reached the ground, unless, of course, you separate them once again, and then it can deliver the same amount of work again. And that is what Helmholtz is talking about on the subsequent pages. 150, 151, he talks about electrolysis, taking water and separating it into hydrogen and oxygen gas, and so on. He goes through a litany of examples that show the transformation of energy from one form to another. And he also talks about electrical and magnetic systems. I don't have time to go through all these in detail. It's a wonderful read. I'd highly recommend you read this. He kind of summarizes this at the end, so maybe I'll end with this. I will not accumulate examples of such relations. In subsequent lectures, we shall come across them. Let us review these examples once more and recognize in them the law which is common to all. A raised weight can produce work, but in doing so it must necessarily sink from its height, and when it has fallen as deep as it can fall, its gravity remains as before, but it can no longer do work. A stretched spring can do work, but in doing so it becomes loose. The velocity of a moving mass can do work, but in doing so it comes to rest. Heat can perform work, it is destroyed in the operation. Chemical forces can perform work, but they exhaust themselves in the effort. Electrical currents can perform work, but to keep them up we must consume either chemical or mechanical forces or heat. We may express then this generally. It is a universal character of all known natural forces that their capacity